This video is brought to you by mywayteaching.com.
In this part, we are going to see simple examples. Example 2. Two charges 3 into 10 raised to minus 8 coulomb and minus 2 into 10 raised to minus 8 coulomb are located 15 centimeter apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. Okay. Let us say this is the line, what they are telling. Okay. And here at this point we'll consider it as O, the charge 3 into 10 raised to minus 8 coulomb, and here it is A, where they're saying minus 2 10 raised to minus 8 coulomb, and these two are 15 centimeter apart. And let us consider a point P here. Okay. And this P be the required point on the x-axis where the potential is 0. Okay, if x is the x coordinate of P, obviously x must be positive. If x lies between O and A, then we can write potential as 1 by 4 pi epsilon naught 3 into 10 raised to minus 8 x into 10 raised to minus 2 minus 2 into 10 raised to minus 8. This point must be 15 minus x, where x is a point that we are considering where potential is 0. Okay, and if you simplify this, we get 3 by x minus 2 by 15 minus x is equal to 0. Okay. Which gives x is equal to 9. If x lies on the extended line OA, then the required condition would be 3 by x minus 2 by x minus 15 is equal to 0. Here the value of x will be 45. Thus, electric potential is 0 at 9 centimeter and 45 centimeter away from the positive charge on the side of the negative charge. Okay. Now let us see one more simple problem. Figure A and B show the field lines of a positive and negative point charge respectively. So this is the figure A and this is the figure B. The field lines of positive charge and the field lines of negative charge. So here what they are asking, let us see. The first one is, give the signs of the potential difference Vp minus Vq, Vb minus Va. Give the sign of the potential energy difference of a small negative charge between the points Q and P, A and B. Give the sign of the work done by the field in moving a small positive charge from Q to P. Give the sign of the work done by external agency in moving a small negative charge from B to A. Does the kinetic energy of a small negative charge increase or decrease in going from B to A? So these are the questions that asking. So first one is potential difference between Vp minus Vq and Vb minus Va. Okay. See, we know that V is proportional to 1 by R. Vp is greater than Vq because Vp minus Vq is positive and Vb is less negative than Va. So we can write Vb greater than Va. Again Vb minus Va is positive. Okay. This is the solution for the first part. Second one, give the sign of potential energy difference of a small negative charge between the points Q and P and between the points A and B. See, the small negative charge will be attracted towards the positive charge, obviously, and the negative charge moves from higher potential energy to lower potential energy. So, the sign of potential energy difference of a small negative charge between Q and P is positive. Okay. And similarly, the sign of potential energy between A and B is also positive. And the third part, give the sign of the work done by the field in moving a small positive charge from Q to P. See, in moving a small positive charge from Q to P, work has to be done by an external agency against the electric field. Obviously, that work must be negative. And the fourth part, give the sign of the work done by the external energy agency in moving a small negative charge from B to A. So, in moving a small negative charge from B to A, work has to be done by an external agency, so it is positive. And the last one, does the kinetic energy of a small negative charge increase or decrease in going from B to A? See, due to force of repulsion on the negative charge, velocity decreases and hence the kinetic energy decreases in moving from P to A. Okay. Now let us study one more important part, that is equipotential surfaces. Okay. What is this equipotential surface? See, this equipotential surface is a surface with constant value of potential at all points of the surface. If you consider the surface, at each and every point on that surface is having the same potential. That is what equipotential surface is. Okay. For a single charge Q, the potential is given by, we already know this, Q by 4 pi epsilon naught R, and this shows that V is constant if R is constant. So, equipotential surfaces of a single point charge are concentric spherical surfaces centered at the charge. Now, electric field lines for a single charge Q are radial lines. We know that starting from or ending at the charge. Depending on whether Q is positive or negative, the direction depends on that. Clearly, the electric field at every point is normal to the equipotential surface passing through that point, and this is true in general for any charge configuration. Equipotential surface through a point is normal to the electric field at that point. Okay. It is normal. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. In order to move a unit test charge against the direction of component of field, work would have been done, but this is in contradiction to the definition of an equipotential surface. There is no potential difference between any two points on the surface and no work is required to move a test charge on the surface, because at every point the potential is same and the potential difference will be zero. And equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around the charge configuration. Okay? Equipotential surface. You can see in this figure, for a single charge Q, equipotential surfaces are spherical surfaces because R will be constant. Electric field lines are radial, static from the charge Q. Okay, for a single charge, these equipotential surfaces are spherical, and here electric field lines are, yeah, they are radial. So here the equipotential surfaces form a uniform electric field. You can see here. Now let us study relation between field and potential. For that, you consider two closely spaced equipotential surfaces A and B. So the first one, A and B, both are equipotential surfaces. Okay, potential at every point on the surface is constant. So with potential values V and V plus delta V, where delta V is the change in V in the direction of the electric field E, and let P be a point on the surface B. We are considering point P on surface B, and delta L is the perpendicular distance of the surface from A to P. Okay, from A to P, delta L is the distance perpendicular from the surface B to surface A. Perpendicular distance. Then imagine that a unit positive charge is moved along this perpendicular from surface B to surface A against the electric field. Then the work done in this process is given by E into delta L, and this work equals the potential difference, that is VA minus VB. Obvious, that is equal to V minus V plus delta V, which is equal to minus delta V. E is equal to minus delta V by delta L. Since delta V is negative, delta V is equal to minus of modulus of delta V. So we can rewrite this equation as E is equal to minus of delta V by delta L. Okay. So here we should consider two of the most important points in considering the relation between electric field and potential. First is electric field is in the direction in which the potential decreases steepest. Okay, the electric field is in that direction where potential decreases with steepest. That's an important thing. And the second point is its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at that point. As we can see here in this equation, the electric field magnitude is given by change in magnitude of the potential per unit displacement, which is normal to the equipotential surface at that point. Okay.